Okay, so I'm going to talk about embodied agent-based models of language learning. So this is a slightly different slant to the talks we've had so far, in the sense that I work just with computer models at the moment, but that doesn't mean that I'm not interested in working with humans. In fact, I'm very interested in working with humans. This is just what I'm up to at the moment, and maybe there's a lot of synergies between what I'm doing and what others like me are doing, and what other people who've spoken here are doing. So it would be super cool to try and explore those in the time we have left. I'll start with like a lot of speakers since Gary gave the introduction. I'll start with Gary's spectrum. So there's a picture of Gary there in lots of points on the spectrum. This happened because I wanted to sort of associate Gary with the spectrum, but then I realized that by doing that, I was putting him in a particular point on the spectrum, which I thought it wasn't my place to do. So I put him everywhere. But hopefully, at least the message is clear. So let's suppose that if on one side of things we have the idea that we do all of our learning through, as humans, we do all of our substantial learning through language, and then at the other end of the spectrum, there's the idea that we acquire most of the knowledge, the important knowledge that we have through sort of direct physical interaction with the world. And this is also an interesting spectrum for the world of machine learning. So at one end of this, you could consider GPT-3, which learns everything just purely from text. And then slightly further along, you could consider that a lot of what's going on in the computer vision community at the moment, which incidentally, and I think you'll be pleased to hear, is becoming much more language centric, right? Like some of the early problems of computer vision are now close to being solved. And what that's leading to is much more semantic problems of computer vision. And that's, of course, where it starts to interface in a somewhat awkward way with language. And then there's a bit where I've been working a bit for the last few years, where not many other people are working, which is language meets embodied interaction with the world, but it's not really the world, it's more like a simulated fake world. And then finally, at the other extreme, there's robotics. But it's probably not fair to lump that in with machine learning, in the sense that most robotics at the moment is not learning based. And actually, in particular, the work on language and robotics involves a lot of hard coded components that don't really require learning systems. But of course, it's probably only a matter of time. So part of the motivation for this 10 minutes is for me to try and excite you about this area where I've been doing a bit of work, and some friends have, but not that many other people. But I want to try and give the impression that it's a useful and very fertile ground for modeling a lot of human phenomena and understanding them better through the medium of modeling. So this is roughly what we do in our work. We have a simulated environment, which comes probably from a computer game, but they're getting increasingly realistic and hopefully better and better. These environments, they feed out data to our agent, and our agent is typically a neural network, a deep neural network. And the environment feeds it out like one time step at a time. And what it feeds out every time step is raw pixels, a vision of the world at that particular time. It's usually a pretty low resolution view of the world. And in the work I've been doing, it also feeds out some language. Now, this is a proxy probably for sound waves, but in our work, it feeds out text strings. And then the neural network itself is any model you might choose to have to cope with this. Obviously, there's many simplifying assumptions here, one of which is that time is sort of separated up into discrete chunks, time steps. And another big one is that the motor actions that this agent actually ends up deciding at every time step, at the moment in the work I'm going to talk about, are discrete. So they could be one of 8 possible movements or one of 16. But it's not continuous control like we have. But anyway, hopefully I'll convince you that at least doing this gets us a little bit further along in terms of the realism of the sorts of models we're able to build. For those of you who are interested in GPT-3, I should just add that one thing we have done, and you could easily do, and this is kind of like a naive thing to do, is to sort of just replace the language encoding part of the agent with a pre-trained language model whose weights have acquired their knowledge just from statistical correspondences in text. And by doing that, you make the whole agent more robust to variation in language. So there's some interesting generalization that can be achieved just by doing that. But I don't think that's a particularly realistic model ecologically. Yeah, so I think it's worth highlighting that almost I could say 98% of machine learning resides in this sort of maroon square here on the left-hand side, and almost nobody's doing anything further right than this. And the work that we did kind of hopefully highlighted why this is maybe an issue. So let's suppose that we're just interested in visual question answering. So visual question answering is modeling a response given some language and a still image of a scene. So in this case, you might get the input or the question, what side is the red guitar? And the answer that the model should be trained to give is on the right-hand side, right? So all humans could do that. And in particular, if we're interested in the ability, so we're not just interested in whether or not a model can learn to fit and learn to respond appropriately to all of the data that it sees in its training environment, but we're also interested in how well it generalizes, how well the knowledge that it acquires in its training set allows it to extend to unfamiliar inputs. So we can probe that by asking it questions about color shape combinations that it's never seen in the training data. So if you look at the table on the right hand side, you'll see we train it on some combination of the colors and the shapes, and then we ask it the same question about color shape combinations that it's never seen. So when we do that with a visual question answering neural network, it masters the training data. That shouldn't be surprising to anyone who knows about these artificial neural networks, because they're very good at sucking up whatever data you give them. But on the held out unfamiliar combinations, it gets about 78%. Now chance here is 50% because there's only two options. So that's quite good, but not perfect. What's interesting is the difference we observe when we give exactly the same task, at least at some high abstract level, to an embodied agent. So this agent's allowed, you can see a video of the agent acting here, it's allowed to move around the world, and instead of asking it a question, it has to actually go up to the correct object and bump into it. So importantly here, the stimuli, the training set and the test set are exactly the same at this high abstract level of what is the instruction, but they're different in terms of the fact that in one case they realized it in one still image, in the other case they realized in terms of a whole temporally extended experience in an environment. But another important detail is that in both cases, the neural network architecture is essentially the same. There's a small difference, right? Because in the case of the agent, the final layer has 8 units because it has to make one of 8 different action choices at every time step. Whereas in the case of the supervised model, the final layer has only 2 units because it has to predict either left or right. But apart from that, the architecture is essentially the same. Well, when we run the models on both of these, we see that the model that was trained to answer the questions generalizes at 78%, but the model that was trained like an embodied agent to go up to the object and actually pick the correct one generalizes at an impossible to better 100%. So this is a kind of really interesting difference, because at least for people who are intent on modeling cognition at the higher level of the way these tasks were defined, they might be somewhat blind to these differences in the outcomes of these two models, right? And it's not just the fact that in one case we might have an embodied agent, and in the other case we might have a static kind of data receiving interface. Because even in the case of 2 different embodied agents, the particular rendering and realization of the environment can make a difference to these outcomes. So we studied this in the context of 2 different environments. One of them was a 3D Unity world, which is not very realistic, but it's quite, it's more, I think you'll agree, it's more realistic on the left-hand side than the right-hand side, which is a top-down 2D grid world. And yeah, in both cases, though, we gave trials, training trials and evaluation trials that were at this high abstract level exactly the same, right? They both contained 3 movable objects, 1 landmark object and an agent, and the locations in which they would appear at the start of every training trial and every evaluation trial were randomized. So one nice thing was that we were eventually able to train the model to do this in the 3D environment. So this is the agent doing it in the more complex, more realistic version of the task. But in both the simple 2D grid world version of the task and the 3D version you've just seen, the stimuli at this high level, abstract level, were exactly the same, right? So during training, the agent was trained to lift the full set of objects in the repository, and these were randomized on an episode per episode basis. And then during training, the agent was trained to put a subset of that total repository on the bed. And then during testing, we verified whether or not the agent could put the remaining subset of objects on the bed. So in order to do this, it needs to somehow sort of like integrate its knowledge of identifying objects and lifting them with its motor control knowledge of how to actually pick something up and put it on the bed. And so, yeah, here's a quick snapshot of what it looks like to do both of these things in the two worlds. The video on the right isn't going to play, but that's not a big problem. Oh, yeah, it might play now. OK, it doesn't matter. So the headline result is that the systematicity, the ability of the agent to generalize in the 3D world was substantially greater than the ability of the agent to generalize in the 2D grid world. So the top two lines you see here are the training performance on the task. And so both of those models master the training data with 100% accuracy by the end of lots and lots of training. But in the case of the 2D grid world, the agent acquires knowledge that is less general. It's less able to recombine its knowledge of how to lift something from how to put it on the final destination object. Whereas in the 3D grid world, it recombines that knowledge more successfully and scores much further above chance on that held out probe. So then we were interested, so this was surprising, although it was kind of a nice reassuring result for those of us who kind of believe in the power of a realistic environment in order to stimulate learning. But we wanted to understand in a slightly more precise way what were the drivers of this effect. And it was actually Jay's student, Andrew, who came up with a really elegant way of sort of bridging the gap between these two scenarios. So one aspect of the 3D environment that's different from the 2D environment is that the agent has obviously egocentric first-person perspective of the world. So in the 2D environment, the agent always sees the entire grid, and it just needs to learn to control itself in the context. So it looks at itself as a square, and it needs to learn to move itself up and down. Whereas in the 3D environment, the agent sees itself from the first-person perspective, and when it picks up an object, that object remains in its view, while other things are outside of its view until it eventually puts it on the bed. So Andrew set up the 2D grid world such that it was able to, it was centered on the agent. So that meant that whenever the agent moved, the frame of reference that the agent could actually take in moved with it, and also restricted its field of view to some degree. And when he did that, he found, there's a couple of interesting observations here. So one is that the training performance goes down. So the task actually gets harder for the agent to solve in the grid world. But the generalization performance, the green line, goes up. So this recovers almost all of the difference between, in generalization, between when we train the agent on the task in the grid world and when we trained it on the task in the 3D world. So that's a little taster of, I guess, some of the experiments that we've been able to do using this new paradigm of a neural network embodied agent in a controlled room. And then I'll just give you a couple of other results that maybe are of interest that relate, I think, to some of the work that you've been talking about so far in the workshop. So there's been a lot of discussions about the dynamics and rate of word learning in young children. So we can study this in our agents. This is a scenario where we consider a word to be learnt if in a room with only two objects, when prompted with the name of that word, the agent picks up the right object. So if we consider that to be sufficient demonstration of acquisition of the lexical item, then we can measure at what rate the agent acquires words. And when we train an agent from scratch, and remember, this is an untrained neural network with random weights, and it's a very large one, so it needs to learn to do a lot of things. In particular, it needs to learn to not move its head in completely random directions. It needs to learn that if you move left and immediately move right, you haven't achieved anything. It needs to learn everything from scratch. And of course, in the red line here, a lot of what you see is the agent learning that, and that takes over 100,000 episodes, right? So very unrealistic. There's absolutely no sort of innate structure or anything in this model. But this is the dynamics of its word learning. But one thing we found particularly interesting was that if we pre-trained a model such that it already knew two words, so it satisfied the requirement for knowing only two words, and then we took that model and we measured how quickly it learned 20 new words. And those 20 new words in objects were exactly the same as the 20 words that we see in the red line. So the green line here, obviously, word learning takes off a lot more quickly when you already know some words. And not only was it that knowing 2 words made the model learn new words quicker, but actually if we pre-trained it on 20 completely unrelated words and then turned it onto the same regime of learning 20 words, that was even faster than prior knowledge of 2 words. So this is probably just an unsurprising fact about neural networks. But the more distinctions you learn to see in the world, and that includes your perceptual system and potentially even your motor system, the more distinctions you have been able to make in the past, the more able this model is to learn new things. And maybe that shouldn't be surprising, but we definitely see those sorts of effects in people as well. And then finally, I know a lot of people are interested in shape bias.
We're really over time. So,
oh, sorry. Okay.
Yeah.
I totally didn't see any. I totally didn't see any time warnings, so I was just rabbiting on. Anyway, that the last stuff was just totally bonus stuff. Sorry, I didn't see that. Okay, cool. Yeah, that's done.
Okay, maybe a quick question, and then we'll go on to the last talk, Jay's talk. And Felix, do you mind stopping the screen share just so we can have the screen real estate? Yeah, there we go.
Can I ask a kind of general question that I think applies to this talk and a couple of others? So you had nicely this 2-dimensional line, but what about the role of caregivers and how much caregivers really shape learning, and especially for language, scaffold language learning? Should there maybe be a 3rd dimension in there, really?
I mean, I'll just quickly say that this is a very rudimentary model and that we don't really have a very sophisticated model of caregivers, right? So for our work, the environment just spits out words and the agent just kind of receives them. So I think we really, we're not very sensitive to that. We're not good at modeling any sort of sophistication in caregiver behavior. So that would, but it would be great to add that to what we're doing. So, but I'll let others respond as well.
So just on that last point before I start, I totally agree with that last point. And I think that, when it comes to anything more, a huge amount of our cognition is culturally specific. And that takes us back to the mathematical cognition discussion, which is a topic that I'm fundamentally interested in, because I think that, it's the caregivers and the school teachers and the academic environment that makes us all have these abilities to think in abstract and complex and interesting ways.